We are still in section 19.5. We're looking at the instantaneous rate laws, the equations that we can use to calculate the concentration of a reactant at any given time in the reaction. And so far we have looked at the first order reaction, integrated rate law, did some calculus, half-life for first order, did some algebra for that. Second order, we did not derive the integrated second order rate law, but did derive the half-life because that's just algebra. And the last thing now that we're going to look at is the zero order or zeroth order. How have I been writing this? Zero order for a generic reaction, A goes to B. And the zero order integrated rate law is going to come from the combining of the equation that we use to calculate the average rate, which is negative delta A over delta T, and combining that with the rate law, which is K A to the zero. And as a reminder, in this situation, we know that the exponent is zero because it's a zero order reaction. So because A to the zero just equals 1, sometimes maybe we would want to simplify this rate law to just be K. So if you did the calculus on this, if you wanted to do the calculus on this, this one's actually pretty easy to do. We would come up with our integrated zero order rate law. And it is the concentration of A at any given time, little t, is equal to negative KT, that's time, plus the initial concentration, A sub 0. Or if you were doing this for a gas, you would say P over RT, that's a capital T, at time t, little t, there's a lot of t's in these equations, equals negative KT time plus pressure over our temperature at the initial time. So those are the two integrated rate laws for the zero order reaction. And just like with the first and second order reaction, if we wanted to, we could plot this with a y equals mx plus b type of a format. We could plot some data. So that graph is going to look like this. It's going to be our y is the concentration of A at any time. Our x is going to be the time. We can see from this that the slope is going to be negative, and the slope is the rate constant. So again, we're going to be able to use graphing the data as a way of one of the ways of identifying whether a reaction is first order, second order, or zero order, because they all graph a little bit different. If we look up at the second order reaction, that is a positive slope when we graph 1 over A at time t. So we get this. And for the first order reaction, if you want to scroll all the way back to that, that was the natural log of A at time t, and that one was also a negative slope. So if you're doing a reaction and you don't know if the reaction is first, second, or zero order, you can actually plot for your concentration. You could plot the concentration versus time. You could plot 1 over the concentration versus time. You could plot the natural log versus time. Only one of these graphs is going to give you a straight line, and that's one of the ways that we can identify the order of reaction. So let's come up with our half-life for this reaction, for a zero order reaction. And as a reminder, when we're defining the half-life, we are going to be talking about T1/2, so that's the time of the half-life. That is the half-life time. And we are also going to say that the concentration at that time, T1/2, is 1/2 of the original concentration, because that's the definition of the half-life. So if we go up to our integrated zero order rate law and we start plugging stuff in, I'm going to start just by rewriting a at time t, 1/2 equals negative kt 1/2 plus a initial, or a sub 0. In place of a t 1/2, we're going to fill in 1/2 a initial. We're subbing that, and that is equal to negative k t 1/2 plus a initial. We can do some easy algebra on this. So let's go 1/2 a initial minus a initial equals negative kt 1/2. And now we're going to end up with 1/2 minus 1. That'll give us a negative 1/2 a initial on the left side is equal to negative kt 1/2 on the right side. Let's get rid of those negative signs. And these half-life equations, we're always writing them with the t 1/2 part isolated. So I'm going to do some magical rearrangement here, and we're going to come up with t 1/2 equals a initial over 2k. And so I took a couple leaps right there with that, but I give it a second and that will absorb into your brain. So this is the equation for the half-life for a zero order reaction.